My name is Wojciech Sadurski, and today I'm going to be talking about the magic of ADB and Android Shell, so the things that we as developers use every day but often don't even realize. So a little bit about me. I'm a technical project leader at TiVo for Android TV. We're working on a video streaming product for Android TV for a retail market, which will be released in the middle of next year. And I'm a technical project leader for that project. I've been in a love and hate relationship with Android since late 2013, so about 6 years now. And I love Kotlin. I love clean, decoupled architecture where things are where they should belong. And I like to understand how things really work, and hence this talk. So every time we hit this small green button, some magic happens. Every tutorial just tells us to just hit it and don't care about what's really happening. But after Gradle with build tools builds our app, it makes its way to the device somehow, and it makes its way to the device with the use of ADB. So what happens is this. ADB installs our APK on the device which we are connected to, be it an emulator or a physical device. And then we call Activity Manager. We ask it to start a selected activity with some parameters, with parameter main, because it's the main entry point, main activity of our application, and with a parameter launcher, because we pretend to have clicked it from the launcher. We want an application to think like it was clicked from the launcher, not from ADB. And this is our example application. I will refer to this example a few times today. So this is just a basic sample with a fab. And once we have our application deployed on the device already, Android Studio somehow magically knows that the application is running, and now it offers us the option of apply changes and restart activity. So how does it happen? It happens through some magic tool called JDWP, Java Debug Wire Protocol, which is used for Java debugging, and it's used for Java virtual machine, Dalvik virtual machine debugging on Android as well. And it runs underneath all the tools that we use every day, so of course we don't realize that it's there. So a little recap. So we have two actors on our scene. We have our development machine, and we have our target device, be it a physical device or an emulator. On our development machine, we have something running called ADB server, and it runs on localhost 5037. And we have something called ADB daemon running on our target device. And both of these things communicate over a USB or IP connection. So we can connect to our device through USB or through IP if they are on the same local network. We don't need a USB cable. So how does JDWP work? So when ADB daemon starts on the device, it creates a Unix server socket of a certain name. If our app is declared as debuggable, so if we have compiled it through Android Studio, regardless of it is of build type debug or release, it has a debuggable flag set to true. So if this is the case, then a special JDWP daemon thread is started inside the process of our application. And we can see it on the debug screen in Android Studio. When we go to the threads pane, we can see the JDWP connection control thread inside of our application. And then when the application is running, the daemon connects to the socket. And if we want to debug the app or know its state, we can forward we can do some magic port forwarding thing, and we can monitor our app, or we can attach the debugger to our application process and debug it. We can track application state using something called track JDWP, and this is exactly what Android Studio does. This is how it knows that our application is running, and this is how this is when it offers us the option to apply changes. And this is an example. If we invoke it from command line, we see some different processes of apps that we can debug. And at the end, we see some process ID of some application. If we then open our application, we see a new process ID appended at the end, and this is the process ID of our application, which was just added to the list of debuggable apps. And then if we close it, it disappears. And yeah, this is how Android Studio knows that our app is running or not. We can see that the state of these buttons change. To the list of the things that happen after we click the Run button, we should add the Track JDWP option. Now we can also debug our app from command line. Of course, Android Studio uses JDWP as an interactive debugger, so it interacts with it through command line, but we interact with it through graphical user interface for convenience, but underneath there is just some instructions passed here and there. So for instance, if we create some method that we want to debug, we may want to set up proper port forwarding and attach a debugger to a selected port. And we can type in that we want the debugger to stop in selected method. So it will stop at the header of this method. And if we type it, it tells us that it has set breakpoint at that point. Then if we click on our floating action button, the debugger starts at the header of our method at the selected line. And then if we want it to step, it steps one line further to the log method, which was inside of the method body. If we tell it to continue, then it does nothing because the application just runs and the debugger doesn't catch it on any breakpoint. And the message queue is empty, there is no interaction. But if we click on the fab again, then we hit a breakpoint again. So this is exactly how the debugger works from the, how it works underneath. But what we see here is the beautiful UI. So another thing, if we click on the debug button instead of run, what happens besides what we already mentioned is a special D flag is added. What this D flag does is it tells the activity thread, or it tells the activity manager to stop the application and make it wait for the debugger. And it's a common misconception to think that when we wait for the debugger, that our app is already running, and we're losing some, and the time is passing by, and we can't attach breakpoints where we want. But it's not true, because this, when we click on debug, our app starts in a place called activity thread. .java, which is a class from framework. This is not part of our app, and this is way before any code from our app is called. So this is even way before application.java constructor is called. So when we wait in such a state, our app has not executed a single line of code yet. So when we click on debug, two things happen. So first of all, we start our app with this debug flag, and we attach the debugger. But if we only click on attach debugger, well, the two former things don't happen. So we just attach the debugger. Now, if you have, any of you has ever been anywhere close to Linux system, embedded system development, you might have interacted with your embedded devices through Secure Shell, SSH. which is somewhat similar to ADB. Well, in fact, ADB is somewhat similar to SSH, but they don't have anything in common, in fact. They just share some similarities. First thing they offer is an interactive shell, also certificate-based authentication, but ADB offers us a lot more because it has deeper integration into our system. Namely, it's, for example, if we create different system images, we may set different paths for different binaries differently. And if we were to use SSH, we would have to guess these paths every time. But in this case, if we hit on ADB install, ADB somewhat knows where to install our app, but SSH would not. So ADB offers us more than just SSH. And SSH is not part of Android by default. We can add it, but it's not there by default. So what happens if we enable ADB debugging and we want to debug our device? So when we connect for the first time, our device asks us to accept a fingerprint, an RSA fingerprint of some device that wants to debug it. And if we say yes, then the debug key is kept is saved in the given path, and therefore the device no longer asks for it. Now, ADB plays a very important role in application development and system development, and it starts and it's part of the init process of Android. And okay, so let's start from the beginning. So when Android boots, first thing that starts is CPU. Then CPU starts bootloader. Then bootloader starts kernel, which initializes drivers and it mounts the root file system. And it starts a very important process called init, which mounts file systems, sets up permissions to these file systems, and then it starts native daemons, and ADB daemon is one of these native daemons. And then Android runtime starts. So ADB starts before Android runtime, before any of the Java system services starts. And therefore, we can use ADB to access shell at the time when Android boots up, and we can, for example, stop the boot process and tinker with our file system in some way, whatever we want to do that there. And then we can ask it to restart the user space, I mean Java-based system services and Java space. So the next thing that starts after native daemons is Android runtime. So so the zygote process, which is the root Java process. So for every Java application and for every Kotlin application, of course, as well, they are forked from the process called zygote, which has all of the framework classes and resources preloaded. Also, every Java system server is forked from zygote, and then and on and on. And after, at the very end of boot process, we land in a launcher. But an important thing to remember is that ADB is available to interact with way before we even see any interactive UI on our device. So we can change some things on our file system at boot up process using ADB. Now, some of the less known ADB commands are, for example, ADB root or ADB shell switch user. Now, if we want to have root access to our device, we want to be able to either run ADB as root or to switch user once we get to the shell on the device. ADB can run in two modes. It can run in secure mode or in insecure mode. For example, on my OnePlus mobile phone, it runs on secure mode, which is desirable. So it has a flag, a special system flag, as secure as with a value of 1. And now, if we look at process states at runtime, we can see that ADB daemon that is running on the device is owned by the user shell, and the shell that we are interacting with when we are typing in these commands is owned by the user shell as well. And if we want to switch user to root or to any other one, we cannot use it. We cannot do it because super user binary is not available on a production device. And the same thing goes with ADB root. If we go out of the shell on Android back to our development machine, we cannot restart ADB to run as root because we're on a production build. But it's not the case on emulator. On emulator, ADB runs in unsecure mode, so it allows us to switch user to root. But if we are not yet root on the same on an emulator, we're again running as shell, and our shell is running is run by the user shell as well. But if we choose to switch user to root, now all of a sudden we're running as root here. And if but then at the same time ADB daemon is still running as shell. But if we choose to restart ADB daemon as root, it instantly starts running as root. And now if we spawn a shell from ADB daemon, then it runs as root as well. And it's also interesting to see that shell's parent process ID is the same as process ID of ADB daemon, which means that shell that we're currently interacting with was started by ADB daemon. Now we can remount. We can want to remount our system partition to read-write. Why would we want to do that? For instance, if we are developing a system application, just like us at TiVo, we are building an application which will be shipped together with a device, so it will be a preloaded system application. And sometimes we get access to user debug builds of system images. And therefore, we can remount a system partition to read-write and pre-install a system app there. And this is how we could do that. And for example, we may want to remove some certain pieces of system applications or add some. For instance, applications which are preloaded on devices from Samsung, for example, or from other vendors, are all preloaded on the system partition. And if for most cases, we cannot remove them from there because system partition is mounted as read-only, and we cannot change it without some effort. We can also choose to reboot our device fully. We can choose to reboot it to bootloader or to recovery, or we can also reboot it to sideload a new system image, which is provided, for example, from Google for a line of Nexus devices. Now, if we get to Android shell, so if we type in ADB shell, we get access to an interactive command line interface inside of Android. And this is very similar to any shell that we see on regular Linux distributions. Therefore, we have access to piping, to output redirection, to files, for example, to background execution, all of the other stuff that we can do on other Linux distributions. Also, we have access to command line utilities provided to us by something called Toybox. I'll get back to it in a minute. We can also interact with Android system services, and we can interact with its file system. Now, what is Toybox? If anybody of you has ever been developing embedded Linux, you may have heard about something called BusyBox. And BusyBox is a set of command line utilities for Linux. And on Android, we have a very similar thing, which is called Toybox. And this is where all of the command line utilities come from. So a process status, for example, or print working directory, or remove file, or remove directory, all of these are not elements of shell. Instead, they are some binaries which are somewhere in the system, which are part of something called Toybox. When we have access to shell, we can also interact with framework utilities like Activity Manager, just like I've shown you several slides before, when we are starting activity using Activity Manager. We can also interact with Logcat and, for example, redirect its output to some file and then get that file from the device to our development machine and email it to someone, for example. And we can also, when we have access to Android shell, we can interact with runtime utilities. So, for example, with Dalvik virtual machine, we can ask it to run a random Java application, which is not an Android application, but it was compiled to Dalvik bytecode. We can ask Android to run such an application, and it can be a server in the web server, for example, if we compile it to Dalvik. There is a very interesting property that we can access through shell, which is boot completed. And if you've ever been setting up a CI pipeline involving Android emulators, you may have heard about it. This is a flag that we can, for example, periodically query for and wait until its state changes to true. And therefore, we know that our system is fully booted and we can install applications on it and perform automated tests on them. We can also set some system property like debug layout, and this will trigger the show layout bounds developer option. And we can also do something called PM hide and hide, which is a command for package manager, which allows us to hide certain packages, and therefore we cannot open them. So, for example, if we are developing a custom launcher for our device, we can hide the default launcher, and therefore the system will not ask us to which launcher we want to choose if we click on Home. There are many interesting things we can find on Android file system. Once you access shell, I encourage you to explore it. For instance, all of the installed APKs from user space reside in data/app, and if we install our application, we can find the APK in its under such path, which corresponds to the package name. We can also extract a file called packages.xml, which contains all of the installation paths for all of the installed applications. It contains all of the permissions for all installed applications, including system applications and pre-installed ones. And this is a thing that we usually cannot access through UI, because usually, in most cases, we cannot see what permissions do system applications have. And they may have some permissions that we may not want them to have, which is, for example, camera or record audio and stuff. We can also, if we're curious, we can browse what user IDs are assigned to certain apps. And we can also find out that system apps usually share a user ID because they are run by a user called system. We can take a look at jobs.xml file, which contains all background jobs which were scheduled both by system and by user apps. We can look at package names. So, for example, if our device's battery life is not doing well, we can look in this place and see if any apps are triggering too many background jobs or something. or if we are using background jobs extensively, we can debug it this way. So, and in the end, I'll also show you how we can force background jobs to be executed for debugging purposes, for example. If we look at file system, we may find interesting things there as well. So, for example, pre-install apps, which belong to system/app or system/priv app. And priv, in this case, does not correspond to private. It's just privileged. And privileged means that these apps can access non-public APIs, so hidden APIs, so APIs that we don't see in Android Studio, and system apps can access them because they are privileged. We can also find very interesting things in the system/framework. For example, framework.jar is indeed our whole framework. So this is a file that gets preloaded in Zygote, from which every Android application is forking its initial process. And it contains all of the files like view.java, context, activity, all of the other files that we are not shipping together with our app. Instead, they are taken from framework. And if we are curious and stubborn at the same time, we can, for example, compare how these files are changed by OEMs, because we can browse how this file look in AOSP. In Android's open source project, we can browse the code of activity or view, but the code that actually ships on some devices may be changed by their manufacturers. For example, it commonly happens that some tiny little details look a little different on Samsung's or Huawei's. This is because these tiny little differences reside in files like view.java, which is shipped on the device. And if we extract the framework.jar file, we can also take a look at internal Android classes, which we cannot access through SDK. For example, if we open activity.java in Android Studio, there is a field called autofill client, which we cannot see how this looks like, because it's not meant to be used by application developers. But if we are very curious, we can take a look at how it looks like either in AOSP, or if we are very, very curious, we can look at how this file looks like on the device that we are developing our app against by extracting framework.jar file. If we go to system/bin, we can see all of the binaries that we can interact with through command line, and on some generic system image of an emulator, there are 27,000 of them, and we can see things like activity manager or audio server, and they are all here, and things like grep, like ps, like ls, like print working directory, they are all here as well. And if we take a look at system/xbin, this is another folder which contains such binaries. And on an emulator, we can find a binary called switch user, which we cannot find on a production build like on my OnePlus phone. This folder is empty. Through command line, we can interact with system services. For example, we can print a list of available system services, and on a Pixel Android 10 emulator, there are 165 system services. Which we can compare to only 65 on an analogical Pixel 3 XL emulator, but Android 4.1. So a lot has changed over the years. And example system services that we can interact with are activity service like package manager service, or even a status bar service, which has its own system service. We can use through command line. We can trigger binder transactions. Binder is an IPC interprocess communication mechanism, which is used for communication between system services and apps and user apps as well. And we can invoke a command service called status bar 1 or 2, and with 1 we can show the status bar, and with 2 we can hide it. And it works like this because to make the long story short, because it's a topic for yet another talk, there's 1 because this is the first method, expand, and there's 2 because it's the second method. End of story. And we can interact in this way with many different services. I've tried to do some fun stuff besides showing and hiding status bar, but I couldn't figure it out how to work with it from command line, but this is just another geeky curiosity. If we're very curious about what processes are running on our Android device, we can invoke process status and show all. And interesting things we can find here are that init, as theory says, init is the first process on an Android device, and indeed it is first, because it has process ID 1. And Zygote, which is a root process for all Java applications, has some certain process ID, and all of the Java applications that are running have parent process ID of Zygote. In this column there is parent process ID, and our application that we are running has the same parent process ID as Zygote. Interesting. To play around with, play a little with Zygote, we can stop it or start it, and this triggers the whole user space to reboot. So it's not a not complete reboot of our device, because basically because we are stopping a parent process, we are stopping also all child processes, and all Java space is restarted. And because kernel has a special check for whether Zygote is running or not, it instantly restarts it. But we can try. We can also, system services are organized in a way that they are exposed for something called system server. And the system server exposes services like activity manager, like package manager. So we cannot find these, if we try to look at running processes and try to find something called something related to activity manager or package manager, we will not find it. These return no results, but instead we will find what is called a system server, which, as we see, has the same parent process as Zygote had. And these system services like activity manager and package manager and all the others are exposed through system server. So they're all running in the same process. And the interesting thing is that if we look at threads, we may find out that system server runs on 132 threads. So all of the 165 system services are running on 132 threads. And also what we can find when we take a closer look at threads is that activity manager runs on 3 threads and package manager runs on 2 threads. I don't know about you, but it's very interesting for me. Have you ever wondered how many threads does a very simple application like this need to run? Any guesses? 1, 2, 3, 5? 150? No, it requires 13. You were very close. Was it a guess or you knew it? Okay. So it requires 13 threads. Why? First of all, it has main thread. And now, we're essentially busting a myth, because it's a myth that Android applications run on a single thread. It's not true. They run on at least 13. We have threads related to the debugger that I was talking about before. We have threads related to garbage collection and to finalizing and reclaiming memory. we have something called render thread, which is what's, again, it's a long story, but it's, so to say, rendering our UI. And we have some open binder threads, which are used for communication with, for example, Activity Manager. And they have their own threads on which if they receive a call to start another activity, then this call is redirected to a main thread, and then another activity is started on the main thread of a given application. So essentially, it's not true that Android applications by default are single-threaded. They are 13-threaded, at least. And if we create a bunch of other threads, in this case 5 new threads, we can see them in this listing as well. So it's also not true, I think it's a common misconception that Java threads are somewhat different than Linux system threads. No, they're not. They're just some handy abstraction of system threads. But in fact, what's going on is system is creating all these threads, not Java virtual machine. And we can also see all these threads in a tab that probably not too many persons look at. When we are debugging our app, we can see all of these threads that are running, and we can stop them one by one, and we can resume them one by one. We can also, of course, the thing which I discovered quite recently, we can also change values of variables when we are debugging. There is another handy command line tool called dumpsys, which allows us to essentially dump state of system services. And the very interesting thing we can do is dumpsys activity manager, dump activities from activity manager and look for the running ones. This is the thing that's missing from the IDE that we use, because we can essentially dump what we can use in Android Studio is layout inspector. So we can dump the state of a single activity and we can look at individual views inside of it. But if we have multiple activities, so for example, if we are getting introduced in a new code base and we get into some activity, there are certain methods to get to know what activity we are in. But this is one of the handiest ones. So we have the currently running activity on top here. So if our app has multiple of them and we get somewhere in the stack, then we may find out that this is where we are. What we can do also is dump status of job scheduler. And we may, therefore, for example, find out that calendar uses 2 jobs, and one of them periodically queries the calendar content provider, and the other one queries notifications provider. I don't know why calendar needs notifications, but well, okay, there are some reasons. And we can also, if we are debugging our app which uses some jobs, we can force our jobs to be executed by using a command job scheduler run -f, which is force, and our calendar with some parameter. And we can force a given job to run. There's a very handy tool, open source, which is called screen copy. Which is very useful. For example, if you can connect to your device over local network, and you can copy its screen to your device, which it works similar to Visor. Maybe you know Visor. So this is a free alternative, free and open source. And it can also be very useful for demo purposes. For example, we use it a lot. If we screencast a demo, we just copy a screen of a device to a machine, which we have Microsoft Teams enabled on, and we just show the screen on Microsoft Teams or through Skype. Okay. There is a very interesting book for those of you who are interested and curious about how Android works underneath, which is called Embedded Android. I read it. At once, I just started and didn't stop until I went to the very end. I was very curious, and it's quite a simple, quite an easy read for such a topic, and I recommend you take a look at it. Thank you.